from the phone that's probably in your hand right now to the actual signals firing in your brain, there's this invisible dance happening all the time, a dance between chemistry and electricity. That's the world of electrochemistry, and today, we're going to pull back the curtain on the science that really makes our modern lives possible. I mean, we use batteries every single day, right? But have you ever actually stopped and thought, what is really going on inside that little cylinder? How in the world does a bunch of chemicals create enough power to run, well, anything? That's the exact question we're going to dig into.
All right, so let's get right into it. When you boil it all down, electrochemistry is all about this amazing relationship between chemical reactions and electrical energy.
So, the formal definition tells us it's a two-part story. On one hand, you've got these chemical reactions that just happen, all on their own. And when they do, they can produce electricity. But then there's the other side of the coin. We can use electricity to make other chemical reactions happen, ones that would never, ever happen by themselves.
Honestly, the best way to think about this is like a two-way street. It's not simple. In one lane, you've got traffic going from chemical energy to electrical energy. In the other lane, it's the reverse. If you can get your head around that one idea, this whole thing becomes so much clearer. So, let's take a drive down that first lane, shall we? This is the really cool part, where we get power out of chemistry. And this whole process happens inside something called a galvanic cell. Now, that might sound super technical, but you know it by a much simpler name, a battery. So, remember our two-way street? This is the downhill direction. The chemical reaction wants to happen. It's like a ball rolling down a hill. It's spontaneous. A galvanic cell is just a clever device we've built to capture the energy from that ball rolling downhill and turn it into a flow of electrons. And what's a flow of electrons? Yep, an electrical current. And the textbook example, the one that really shows us how this works, is called the Daniell cell. It's a classic. It uses some pretty basic stuff, zinc and copper, and it's the perfect model to see exactly how this power generation happens. Okay, so how does it actually work? Well, it's basically a three-step process. First, at one end, the anode, the zinc electrode starts to dissolve. As it does, it releases a bunch of electrons. Think of it as letting them go free. Second, at the other end, the cathode, you've got copper ions just hanging out in the solution. They see those free electrons and they grab them. This turns the ions into solid copper. And third, and this is the magic part, that journey of electrons from the zinc to the copper, that's your electron highway. That's the electrical current we can use to power stuff. Okay, so that's how we get electricity from chemistry. Pretty neat, right? But what about the other lane on our two-way street? What happens when we flip the switch and use electricity to force a reaction to happen? Well, this is where we meet the other kind of cell, the electrolytic cell. Let's put them side by side. A galvanic cell, our battery, has a spontaneous reaction. It wants to happen, and it produces energy. An electrolytic cell is the complete opposite. It takes a reaction that does not want to happen and uses outside power to force it. The absolute best example? Recharging your phone battery. You're plugging it into the wall to use electricity to run that chemical process backwards. Let's go back to our Daniell cell for a second. It naturally wants to produce about 1.1 volts of electricity. This is the perfect way to see how we can flip the process. So imagine we apply an opposing voltage from an outside source, but it's less than 1.1 volts. What happens? Nothing much. The cell's own chemical push is stronger, so it just overpowers our little external push. Electrons keep flowing from zinc to copper, just like a normal battery. But now, what if we crank up that external voltage so it exactly matches the cell's 1.1 volts? Well, everything just stops. It's a perfect standoff. The external electrical push is perfectly balanced against the internal chemical push. No electrons are flowing, no current, no reaction. The whole system is just frozen in equilibrium. And here's where it gets really interesting. What if we push that external voltage even higher, say past 1.1 volts? Now we've completely overwhelmed the cell. We force the reaction to run in reverse. Electrons are now ripped away from the copper and shoved onto the zinc. The copper starts to dissolve and the zinc starts to build up. We have literally forced the uphill reaction to happen. Our battery, our galvanic cell, has just become an electrolytic cell. So this all begs the question, right? How do we know which reactions are downhill in the first place? And how do we figure out how much voltage they'll produce? Well, there are rules to this two-way street, and it all comes down to something called electrode potential. The key concept here is something called the standard electrode potential, which you'll often see written as E naught. Basically, it's a number, measured in volts, that tells us how much a substance wants to gain electrons. The best way to think of it is like a power ranking for chemical reactions. It's a league table for chemistry.
So if a substance has a high positive potential, it has a really strong desire to grab electrons. Just look at fluorine, way up there at plus 2.87 volts. It's the biggest electron hog there is. It's the strongest oxidizing agent. On the flip side, a really negative potential means the substance would much rather give up its electrons. And down at the bottom, you've got lithium at negative 3.05 volts. It's desperate to get rid of an electron, making it the strongest reducing agent. And you'll notice hydrogen right there in the middle at 0. That's our baseline, our reference point for the whole scale.
Okay, so let's bring it all back to our Daniell cell. The standard potential for copper to gain electrons is a positive 0.34 volts. The potential for zinc is a negative 0.76 volts. To get the total voltage of the cell, you just find the difference between the two. So you take the more positive one, 0.34, and you subtract the more negative one, negative 0.76. And what do you get? Bam, 1.10 volts. The power ranking perfectly predicted the voltage of our battery. It's not magic, it's just math.
Okay, this has been a lot of chemistry, I know. But this isn't just some abstract science experiment. Understanding this two-way street between chemistry and electricity is absolutely fundamental to pretty much all the technology that defines our modern world. I mean, think about it. All the batteries that power our laptops, our phones, our cars, that's electrochemistry. The huge industrial processes that produce essential metals like aluminum, electrochemistry. Manufacturing vital chemicals we use every day, you guessed it, it's even used to stop giant bridges from rusting. And get this, the very nerve signals that are letting you process what I'm saying right now, that's an electrochemical process happening in your own body.
And that brings us to a really important point for our future. There's a quote from the material we're looking at that says, "The reactions carried out electrochemically can be energy efficient and less polluting." And that is huge. Why? Because you're going directly from chemical energy to electrical energy. You're not burning something and losing a massive amount of that energy as wasted heat. This efficiency makes electrochemistry absolutely essential if we want to develop greener, more sustainable technologies.
So, as we look ahead, as our world demands more and more power, the principles we've talked about today are going to be right at the heart of the solution. From designing the next generation of super batteries to creating cleaner ways to make things, it all comes back to this. And it leaves us with a pretty fascinating question to think about, doesn't it? What new chemical reactions are out there waiting for us to discover that will fuel our future?